hear me okay? Good. Couple things I wanted to say before I started. First, I wanted to say I was very glad that there was actually a break of an hour lunch between the last talk and mine, because I don't think that my comedic timing is going to be quite as spot on as that. So a little bit of space from that act to follow. Thank you, Kelsey, for the introduction. And also just to say that it is quite an honor to be up here. It's a bit humbling to share this stage with some people whose names I've been following for a long time. And I don't consider myself much of an expert in anything, but I have been playing around with Go and been trying to do some data snarfing and data crunching for the last year or so. And going to share what me and my small team of folks have been working on. Hopefully you find something useful and enjoyable in it. So this is Adventures in Snarfing and Crunching, starring Hecka. I am an engineer for Mozilla Cloud Services, and as Rob Pike was saying earlier today, we used to just be the Mozilla Services team, but now we're Cloud Services because that's what you do these days. Interesting thing about Cloud Services is that even though it's cloud, you still need cloud servers. So yes, we have a lot of them. Some of them are physical, some of them are virtual, but we have to have our services run somewhere to support our phone operating system and our browser. And these cloud servers, they produce a lot of cloud data. And this was a problem that I started to tackle about a year and a half ago. One of my bosses came to me and said, Rob, you know, we're writing all these services, they're producing all these data, they're running on all these servers, which are also producing all these data. Maybe you want to take a look at that problem and see how we might deal with this fire hose and make some sense of it. There are many flavors of cloud data, or as we like to call it, data, running on these servers. We've got log files, and among the many flavors of tools, you also have many flavors of data. You have many tools to deal with this data. So you've got kind of the general logging problem space with tools like R, syslog, ng, and logstash, and Splunk, and et cetera. You've got the kind of numeric time series data toolkit, statsd, graphite, ganglia, et cetera. You've got kind of sliding window, common event processing, simple event processing things, anomaly detection, real-time processing. You've got monitoring tools for when you're doing your real-time processing and you notice that someone needs to be notified about something, and the tools that go along with that, Nagios, Xenos, et cetera. You've got app instrumentation, you've got New Relic tools, you've got kind of bespoke timing and other data gathering that the engineers are actually putting in your application service code. And then you've got metrics that the servers themselves are generating, the stuff that your ops people care about. How much RAM am I using? What do my file systems look like? What the CPU load look like, et cetera, and et cetera, and et cetera, and et cetera. There's a lot of different types of data. So when we were looking at this problem in the general sense, we realized that even though there's lots of different types of data, all of this adheres to basically one simple pattern. You get data, you transform and or transport that data, and then you deliver it. And that's obviously a bit reductive, but if you look at all of the different tools that we saw in this slide, they all basically follow that set of steps. So we started by kind of playing around with some of those tools and experimenting with them, and we found some interesting ideas in there, and we actually decided to take it a little bit farther and drill into more detail on this on this pattern, rather. So drilling into those three steps in a little bit more detail, when we talk about getting data, the first three here have to do with that, where getting data is first accessing some stream of bits from somewhere, be it over the network, on the file system, generated by a process that's running on your machine, some stream of data coming in. Then you want to identify and split that data on record boundaries. Now, you might be having UDP packets, and it's like one record per packet. That's a simple, trivial case. But you might have streams of data coming in that have specific framing around them, and that's a particular thing where you need to divide it up into the records. And then, if you're going to do anything meaningful with this data, you need to parse those records and do some decoding and convert them into a common format that you can actually work with inside of your tooling. Once you've got this common format, then there's some work that you can actually do. You can route your records to the appropriate consumers. Some of those consumers are going to be doing crunching and processing on this data in real time. And as you process the data, you might be generating new data, generating new messages, again in that common format, because we're kind of inside our controlled zone here. But then eventually you do want to talk to the outside world again. So you start generating new messages, or I'm sorry, generating from the common format to some other serialized format, so that then you can finally push it out to the world again in some form or another. That is the basic design that we ended up putting together for Hecka. Hecka, just as an FYI, is specifically targeting the problem of doing real-time data processing, grabbing data, pipelining it, letting you examine it as it flows, and then it's meant to interoperate with and deliver to data warehousing solutions and offline analytics, but it's not meant to replace those. So it would be used in conjunction with some kind of big multi-terabyte backend place where you might be pushing your data. But you notice this first input splitters decoders, that talks about that data input process. And we found that some of the other tools that we were looking at had this idea of like breaking a pipeline down, but we refined it, I think, to what's a pretty good sweet spot at being able to manage these things in a very reusing the code well way. One of the tools we looked at originally was Logstash. Raise your hand if you use Logstash. Logstash is a great tool, solves some really wonderful problems. We actually started out prototyping this system using Logstash, and we stole a lot of really good ideas from it. It wasn't up to what we wanted to do with it, unfortunately, as far as scaling, and we looked at trying to improve it, and we didn't think that it was actually going to be up to the job at all. But we did steal some of the ideas, but then we extended them. So with Logstash, you might have like a statsd input, or you might have an input. You basically have a different input for every different source of data that you have. But we didn't want to have to reinvent the wheels. We started doing that way, and it's like, oh, we're getting data from the file system in this format. We're getting data from the network in this format. We're getting data from some process in this format. We use protocol buffers a lot inside of Hecka, and we wanted to be able to reuse the protocol buffing parsing code regardless of if we're reading a stream from the file system or if it's coming in over a TCP stream. So we added that here on the input section by breaking that up into further steps, and we've actually found that to work extremely well. The inputs only deal with the raw low-level interaction with the protocol or the medium itself. Then we send it to a router, which I'll talk a little bit more about, and the router determines which filters and outputs it's going to go to. And this design here, where you see just outputs, is accurate as of today, but I'm about a couple more files full of tests and some documentation away from landing a new branch I've been working on, where we introduce a new plugin for encoding, which provides the same kind of separation on the output level. Our TCP output does some queuing to disk and some reconnect intelligence. So if your connection breaks, common TCP problem. We didn't want to have to solve that problem for everything that we talk to that does TCP. So we separate out the serialization step and then just have the output deal with that issue. Now here's the place where, one thing that I want to give you a disclaimer on is that I was planning on doing a demo, and unfortunately we had some tech problems, so I'm not on my own machine. We're not going to be able to do that at this point. But I'll drill in a little bit to how Hecka is put together, since this is a Go conference, and we're interested in learning a little bit more about how Go works here. So our shared format, the common format that we use inside, is a message struct that is driven by protocol buffer serialization. We kind of wrap that around a pipeline pack struct, which contains kind of internal Hecka bookkeeping details. And then we have plugins that deal with these pipeline packs. So all the plugins expect to get packs in on a channel, and they run in their own Go routines. And this has actually proven to be a really nice way to manage the concurrency for something that can get pretty complex at times. The packs flow through this pipeline over channels. Each one has an input channel that it just pulls from. But then the plugins themselves decide where is this supposed to go next. we managed to hide a lot of the complexity of actually interacting with the Heka pipeline. So if you wanted to write a plugin, you could do so in Go, and really all you have to do is implement a very simple interface, and then we will automatically wrap it in a plugin runner for you that handles the Go routine lifespan, handles giving you access to the channels that give you input, handles giving you access to like timer, ticker channels, and basically various things that let you do what you want to do with it. And then finally, we have found that this tight coupling pattern of having a plugin in a single Go routine does help to keep the concurrency sane in what is a highly concurrent system, potentially doing lots of different things at once. I like to think of each one of our plugins as its own internal event loop. Of course, inside a plugin, you can do whatever you want. You can spin up multiple Go routines, and sometimes we do that. But one thing that, Go has amazing concurrency primitives. They're really easy to use, really easy to understand, but there are no guardrails. Ultimately, you are still dealing with multiple threads of execution with access to the same mutable state. And you can shoot yourself in the foot just like you can with any other language that allows those points of access. So it's really up to the developer to maintain that complexity and try to encapsulate it. And I find that tightly binding a Go routine to a single struct and making sure that that works and having it all driven by a single select loop over channels means that now I don't have to worry about race conditions and concurrency issues inside of that struct itself. And it actually frees me up from a lot of cognitive load that I would normally have to deal with in a mutex-based system. So after the decoding, most of the packs will be handled to Heka's internal router for delivery. And to handle this, we gave each filter and output the ability to specify a message matcher. We implemented that using a simple YAC grammar that we designed. So basically, you can say, OK, give me all the messages where the type is my message type, or the payload contains this substring, or it even supports regular expression matching. Of course, the more complexity you add to your matcher, the more performance it hits. But you can do lots of complicated things here. It turns out to be very fast. In the simplest case, we can match on a message through our router in about 10 nanoseconds. If you add kind of more like simple string matching, it maybe goes up to about 100 nanoseconds. But even with the most complicated regular expression matching, we find that under 1,000 nanoseconds is how long it takes for one of these matches to hit. Now, there's a lot of room for optimization here. We're not doing this in any kind of a tree. It's running through each one independently. If two plugins share like 3/4 of the same matching component and then a little bit different at the end, there's a lot of ways that we can join, but we're actually still seeing throughput to where that hasn't been an optimization that we've needed to tackle yet. So we're happy with the performance at this point. The matchers themselves also run in their own Go routines and are also fed via input channels. And then we get on to sandboxes. So we chose Go for this, and I'll go into the reasons why in a little bit. But it's important to notice that Go didn't solve every problem that we had. And so for that reason, we brought in a very nice little embedded higher-level interpreted language called Lua. And some of our plugins, our sandbox plugins, where actually the plugin themselves is still written in Go, but for filters, decoders, and encoders, all of the important logic can actually be written in Lua. This has given us a lot of wins, actually. First of all, it's sandboxed. So we can actually open up some of these to untrusted coders, or if you want to do some new processing on a production Heka that's doing some important stuff on the side, you don't have to worry, I made a mistake in my crunching code, and now I'm going to chew up all the memory of the machine. I'm going to eat up all the disk space or all the CPU usage. So we can actually limit those and shut a sandbox down if it starts to misbehave. The filters support dynamic loading. So if you want to introduce new running code into a Heka instance, you can just shoot it into a running Heka without having to reconfigure, without having to restart the process. And unfortunately, that's what I was going to show you in my demo, and I'm not going to get to. It's extremely fast. Lua, as far as an interpreted scripting language, is screamingly fast. I've been shocked and amazed. In fact, especially it's fast for text parsing, which is something that I found that Go is actually not particularly fast at due to a lot of cost of reflection when you're trying to figure out, if you do texting of JSON and you're doing integers and reflection, there's a performance cost. We've actually found that for JSON parsing and for pretty much every text parsing job that we've done, it's like about 5 times faster to serialize the message to protobuf, pass it over to Lua, do the parsing in Lua, and then protobuf back and send it through to Go again. So and then you get a lot more flexibility on top of the performance because you have a full Turing complete thing. If you want to, I like what it's doing, but I want to tweak some of the decoding a little bit, you have the ability to do that very easily. We also found that Turing complete in that is a lot better than like complex config language. If you've got, say you've written a Go plugin that's going to take JSON and map it to a message structure, and you say, there's some dynamic fields here, so I want to specify this is a new field on the message. This is going to be of integer type. This field has this amount of metadata that I want to include. Go itself is, the binary is compiled, it's there. Any flexibility that you want to have to have pre-coded into your system, and then you have to have these complex DSLs in your configuration to account for that. By punting over to a Turing-complete language that actually lets you do whatever you want in there, we can just say, here's the code to do it, and this does most of what you want, and if it doesn't do everything you want, you just fork it, make a little change, and you're good to go. And finally, part of the reason why parsing is so fast in Lua is that someone was saying earlier that Rob Pike was saying, there's much better tools to use than regular expressions for parsing. Lua exposes one of them called parsing expression grammars, or LPEG. LPEG is a really amazing way to deal with just about any text parsing problem by defining a formal grammar in code. What's nice is that a lot of times RFCs are presented with an eBNF grammar, and so we find that you want to handle this RFC, go look at the RFC, there's a grammar right there for you. Porting it to LPEG is almost trivial. It's like a line-by-line write. Another thing we found with LPEG is that it composes itself much more nicely than regular expressions do. A lot of times, people say, I want to parse my Apache logs. I want to parse my Nginx logs. I want to parse my HA proxy logs or my rsys log output. All of those daemons have flexible log output format. If you go to your Apache or your Nginx config, there's a place where you're like, here's what my log format is. And there's a whole DSL in there that says, here's the timestamp, and here's the status code, and here's the this, and here's the that. So it's not just a single format. So when people want to parse it, you have to define how it's going to be output on the daemon side. And then you usually go and use regular expressions on the other side to say, and this is how I restructure that data and turn it back into something that I can use out of the unstructured text that I'm getting. Because LPEG is composable, we've actually been able to do some really interesting and, to my mind, really impressive things. Like we wrote a metagrammar that actually parses the Nginx config format, and from that constructs an LPEG grammar that matches the output that format gives you. So if you want to parse your Nginx configs in Heka, the way that you configure Heka is go to your Nginx config, copy that log format line, paste that into your Heka configuration, and you're done. Whatever you're emitting is now being parsed. And LPEG gave us the flexibility to do that in a way that less robust parsing tools wouldn't really be able to do. And that's been a huge win for us. The initial climb of getting that done in the first place is considerably more work than a one-off regular expression. But the first person who does it has now done it for everyone. And that's what we're finding is that as we've built up a corpus of these decoders, the amount of work that we have to do is becoming almost nil. And as you might guess, it's screamingly fast. So this is where we were going to see it, and we're not, unfortunately. But now I'll get into a little bit more of kind of the case study of this situation. Why did we choose Go for this project, and how did that work out for us? There were a number of factors that contributed to our choice of Go. The first one was performance. Most of the other tools in this space that we found initially, have been written in higher-level languages. Logstash was one thing we initially were taking a look at. That's in Ruby. It runs only on the JVM. And the promise of something close to C speed in a language that didn't have a lot of cognitive load was definitely something we were excited about. We wanted a lightweight deployment environment. I'm looking at you, JVM. The concurrency primitives were attractive, and as you can see by the way we've put this together, they actually fit this application structure very well. And there was some risk management involved. When we started this, Go was pre 1.0. Go is still quite nascent, but it's a lot safer a bet now than it was a year and a half ago when we picked this up. And when we first started, my boss was like, yeah, this is great. I'm waiting until the first time the runtime just screws us. And we've got something running in production and it all blew up and the stack traces point to lines that don't exist. And we've been running this in production now for about a year in various iterations, and we're still waiting for that time. So it's one thing I would actually applaud Go for considerably. For such a young language, the runtime stability and the tooling coming out of the gate was really, really exemplary. And the risks that we did take paid off. But we still wanted to manage those risks, so Hecka was a good choice because we were replacing existing infrastructure / back-end tooling that only we were depending on. So in other words, we didn't bet the farm on an untested technology that was like user-facing and our business depended on. We kind of said, let's manage where we're going to expose our risk to this new technology, and we wanted this place to kind of explore, and so we did, and it ended up working out really, really well. A lot of people ask me, I don't think Rust is actually a head-to-head comparison with Go. There's some similarity, but there's also some fundamental differences. But because Rust was written at Mozilla, a lot of people say, hey, why didn't you use Rust? And this is the answer. We looked at it. It wasn't ready at the time we started evaluating it. And frankly, a year and a half later, it's still not ready. It's much closer to ready. 1.0 is targeted to happen by the end of the year. It would be a good choice for this type of an app. Not all places where Go would work well do I think Rust would work well. I do think Rust would be, this does fit in Rust's sweet spot as well, but it's several years behind Go in terms of maturity. And also the cognitive load to get up to speed with Rust is considerably higher. So what's been awesome about the fact that we chose Go? See the last slide. All of those things that we thought would be good did turn out, in fact, to be good. The performance is, several orders of magnitude better than the tools that we were replacing. On my laptop, I can process about 400,000 messages a second through the routing and through the protobuf encoding and decoding and counting them, and et cetera. And that's actually without us being as careful as we could have. I'll talk about some of the gotchas in a minute. But I'm impressed with how we've gotten. We haven't done nearly as much optimization as we could, and it hasn't become a priority to do so. The tooling, as I said, is really exemplary. The first time you fire up web in the preprof tool and you see your little SVG graph pop up is like enlightenment. Interfaces, the ad hoc interfaces, the ability to implement them without having to declare that you do. Some people complain about it. I think it's amazing, and we have used that much to our benefit. The built-in kind of back pressure failure conditions that the channel metaphor gives you really works well for making sure that you don't keep accepting requests that you can't handle, and we push our back pressure to the clients when we have to. And then the platform has really improved a great deal underneath us as we've been going. And static linking, it's great to be able to push a single binary out. And then CGO, because we are wrapping Lua, which has a really great C interface. Doesn't have a native Go interface, or not one that we wanted to go with it anyway. It was great, and we did find that CGO was pretty easy to work with. So more interestingly, what's been not awesome about Go? Static linking. Static linking is great from an ops perspective, and it does mean your deployment story is a lot easier. However, when you're building a heavily plug-in-based system, you can't introduce any new code without recompiling the binary and then redeploying. Dynamic linking for us to be able to wire in new plugins would definitely be handy. We routed around that with Lua, but that still doesn't solve all the problems. CGO, while it is really quite easy to use, we have found that it has some painful spots, and I'll talk about those a little bit. CGO interactions cause a lot of memory copies. So when we're passing things back and forth from Go through C to Lua, protobuf serialization, lots of memory copying going on. It's hurting our performance a lot more than we would like. C flags and LD flag directives in your Cgo comment code at the top, they require full paths. So we're actually building Lua libraries as part of our build structure. We actually have like .go.in files, so we can kind of dynamically insert where those includes are going to end up, and that's been a little bit painful for us. We haven't been able to get static linking on Windows to work, and that's caused us some testing pain on Windows. You have to move DLLs around to make sure they're going to be where you expect them to be. And we found linking to be finicky on Windows and OS X. I've had a lot of cases where like someone will say, oh, I'm trying to build your tool on my Mac and it's not working. And I pull up mine and it's like, well, it is. It's like, well, different version of Clang, different version of OS X. And Linux, we have not found this problem. Linux seems to be like the first supported C linking, and it's actually been pretty solid. But on both Windows and OS X, we found that, shake some chickens, some rattles, sprinkle some water there, and hopefully it'll work out. Also, test scoping has created a little bit of pain. You can't always test everything that you want to from the outside of your package because of the package scoping rules. But then you also can't export test code from within a package. So either you're left with dumping kind of test droppings into the publicly exportable part of your actual production code, which just feels a little dirty, or you end up duplicating code in a few different places. And we've just found that we can't put our tests together quite as well as we'd like to. Packaging, I respect Go's decision to not make a concrete not take a solid stand on more robust packaging than what we get with GoGet. And I think that's fine. We've actually managed to handle our dependency pretty well. We just use CMake and have a pretty pretty robust build structure around everything. But it does feel like the environment should meet us just a little bit further than it does. And I do trust that over time the community will come up with something that will do that. But it's been notably missed. Yes, generics would be nice. Some gotchas that we've hit. Mine the copies. We use strings in the high performance talk earlier. There's a lot of talk about doing unsafe casts from bytes to strings, byte slices, using byte slices with no allocation. Yeah, we were not as careful with that as we could have been from the get-go. And so if you really are in a high performance situation, notice, where am I using strings? Where am I using byte slices? It's always a mem copy to convert from one to the other. Strings are immutable, so anytime you try to modify what's contained in a string, you're going to be doing an allocation and a mem copy. Interface is better than struct in most cases. Usually you can, it's some technical debt, but I've had several times where I'm like, oh, design a struct and start using the struct throughout my code and then realize, oh, this really should have been an interface. I should have thought about it a little more. And then you kind of go back and write an interface and go and change it around. Package bloat, we've gotten past that, but originally the ability to just kind of put a bunch of things in a single package is very easy and very tempting. And we had a bit of a package get-in where we went in and kind of split things out. Doing it from the beginning is smart because it actually makes you manage your scope more carefully too, and it actually makes you not cheat and forces you to use interfaces instead of structs when you should. Again, there are no guardrails. The concurrency primitives are great, but you have to mind your own safety. And it is absolutely possible to crash your system and to get Heisenbugs by mutating state from multiple places at the same time. And that's all I have. This is some contact info. I wanted to say I will be here for the hack day, and I'll be happy to give demos and probably work on the thing. And if you have any questions for me, come up. And thanks so much for your time.
Two questions. We've got time for 2 questions.
One right here.
Hi. I really think it was a great talk, and I'm interested to try Hecka at some point. But I would like to know how you are using it inside Mozilla, if that's possible to tell.
Sure. So we've started using it originally kind of as a data router behind Marketplace and behind the sync services. One of my colleagues here from OPSEC has been playing around with it. The operations security team has actually been looking at it, evaluating it, I think starting to roll it out as kind of our primary log shipper tool. Our goal with Hecka was basically, we want to install it on every single node we have, and we basically want to replace 2 or 3 other services that would have been running anyway. So we want to replace, and you know, we're slowly kind of like infiltrating and getting out there. If you're using statsd, great. You can drop Heka in instead of statsd as a transparent replacement. Still takes in the statsd data, still sends your data out to Carbon, but you also get the ability to do real-time data analysis. What I didn't get to show you is that these Lua filters, you can inject them into a running Heka, and then you can also start outputting graphs in real time of that data on a dashboard that's served over HTTP. So, and we're also rolling out in Lua some like anomaly detection math libraries. So we're trying to make it where it's like, oh, you're using the statsd data, great, but what if you wanted to like monitor that and start sending output to Nagios when something goes wrong? So we've got graphs with annotations, and what we've done is with Marketplace is all the statsd data that was coming through there, we've now got it firing on to these graphs, and the graph annotations are showing up when we think a notifier should show out. We've been kind of tweaking the math until we see the number of annotations that we want to, and get rid of the false positives, and now it's like, great, turn it on. Now we've got notifiers on our statsd data if all of a sudden the number of 500s go through the roof, or the number of 400 or 200s, you know, plummet unexpectedly. Last question.
Hello.
Thanks. Should I or should I not use Heka for data that I can't afford to lose?
You can't trust Heka at this point to be the sole owner of data that you can't afford to lose. We do hope that's kind of our long-term vision, is to grow into more kind of like Storm or Kafka-esque delivery guarantees. But we're definitely not there yet, and that's not on the shortest of lists. However, you can still get a lot out of Heka for that, and what we've basically been telling people is go through the file system. A lot of data, if like you don't want to send it over UDP to us, you don't want to send it over TCP to us, you know, yes, there's a pipeline here and stuff might get lost, but we actually do a really good job of like tracking how far into file system files we've gotten. We've got a really nice abstraction layer that lets you define, these are all of my directories where files might be. We use log streams instead of log files, and we can handle sophisticated file rotation schemes. So if you've got data that you really want to get Heka's benefits for, but you don't want to lose it, shoot it through the file system, treat that as your canonical copy. Anything goes wrong down the line, it's like, great, go back to the files, move your cursor back a little bit, and you're off to the races. But we are definitely not giving delivery guarantees at this point. Thanks again.